For this video, I'm going to look at problem 39 from chapter 24. 39. So in this problem, you have two plates that are not quite parallel. So you start with a parallel plate capacitor and you tilt one of the plates by a small angle theta. And we are asked to determine a formula for the capacitance C in terms of the area, the distance between them, the original distance between them, and theta. And we are going to assume that the plates are square. And they give you a hint. Imagine the capacitor has many infinitesimal capacitors in parallel. So this is our configuration. So I have a plate here that's positively charged. This is all the book. And distance d away from this, I have another plate that's negatively charged. Okay. So presumably they have the same charge. So this is plus q. That's minus q. They start with the normal capacitor with the distance d between them, and then one of them gets tilted by some angle theta, and these have surface area A, and we are told that these are actually square, so we can just call this, L by L, something like this. Okay? And the hint they give you is that to think of this as infinitely many infinitesimal capacitors that are connected in parallel. So you can divide this into little parts. Just these little parts over there, infinitely many of them, and we are going to just calculate the capacity. We can calculate the capacitance of each of those little capacitors and add them up because they're connected in parallel. Why are they connected in parallel? Because these are conducting plates, so these are equipotential surfaces, so all those little capacitors have the same potential difference across them, so they are connected in parallel. And we can just, if we can calculate it for one, then we can calculate we can just take an integral to sum up all those capacitances. Now this is not an easy problem, it's a bit tricky. With the hint given, it's not that hard. We can take that, but I would like to approach this problem without the hint itself. Right? So I will solve it in some way, and then I will try to solve it the other way. Now, my general strategy that I followed in class to calculate the capacitance was writing the definition of capacitance. So this is Q divided by delta V, and somehow expressing this Q through electric field and so on and so forth, and then getting some delta V dependence, and delta V should cancel out. I'm going to end up with some factors that just depend on geometry. Right? This was our general strategy for the parallel plate capacitor, for the spherical capacitor, cylindrical capacitor, and so on and so forth. Yeah, so let's see if this works here. Now, how is this Q going to be distributed over here? So that Q is going to be some sigma times some surface area, okay? But that sigma, the surface area density, is not going to be constant, right? So if the plates are parallel, it's of course constant, it's just uniform. But when you tilt this, some of these charges will have a tendency to accumulate at the near side. Now why? Because these positive charges, if they are over here, then they are closer to the negative charges. So they want to be over here, but at the same time, they of course get repelled by the positive charges in the plate, so they can't all accumulate at this end point, because there's some internal repulsion coming from the positive charges. And similarly for the negative charges, they want to be here because then they are closer to positive charges, but they can't all be there because this is not going to, it's not going to work. There's some internal repulsion from negative charges, right? So what will happen is that there is going to be some sigma that depends on our position on the plate, but it's not going to be constant. It's not going to be something uniform. Now, to make this a bit more concrete, I'm going to draw a coordinate system. Okay? So let's draw something like this, x here, y here. So my sigma is going to, in general, depend on the position. Now this is true for both this one and that one. Now you might be thinking, okay, but as I tilt them, their y coordinate is going to change. But if you recall the small angle approximation that we used in one of the used problems, the difference in height, the difference in this direction is going to be second order in theta. So if this theta is small, we can neglect that. So we can assume that even though they're moving away from these other charges, they're still going to be at the same height. So their height, of course, changes, but that changes second order. Okay, so the same thing is going to work for this plate as well. In fact, this part of the reasoning is essential to solve it with the hint given in the problem. Okay, so that is going to be my sigma. Now, how will I express this Q in terms of sigma? That Q is going to be sigma times dA. Okay, so I add this up as I go from one side to the other. So y equals 0 to y equals L. These are square plates this way, so their height as well as width are both L. Now, if I just draw that square plate, let's try to draw this here, okay, L by L, I'm going to divide this into little strips. Okay. This being my y coordinate again, this perhaps being the z coordinate in this case. As I go along the width of the plate, the sigma is not going to change, right? I'm just going back and forth over here. The sigma remains the same. As I go farther from this endpoint, the sigma is going to have some y dependence. So over this distance, this is not changing, so the sigma is constant. Over this axis, it's just going to change. So what is the ADA is the area of one of these little strips, and that is going to be L times dy. As I move along, the thickness of the strip is going to be dy. The length of the strip is L, so the area of the strip is L times dy. So let's write this down. Now I can just make this 0 and L. This is going to be sigma of y, L times dy. Okay, now what is that sigma of y? Well, that sigma of y, I want to connect this to the potential difference somehow. So I want to do that, I need to write this in terms of the electric field, but I know what it looks like. These are conducting plates, so on the surface of a conductor, the electric field strength is just sigma divided by epsilon naught. So the electric field strength, which is also a function of y, is going to be sigma of y divided by epsilon naught. Now, why is the electric field strength is a function of y? Because as we move further, the electric field must be getting weaker. Why? Because these two are equipotential surfaces. The potential across this is the same all over, and the potential across this is the same all over. So the potential difference between these 2 points must be the same as the potential difference between these 2 points. Okay? But the only way that this can happen is if the electric field over this region is weaker than the electric field over this region. Otherwise, the delta V E times D, or let's say call this not E delta X, because D has a special meaning here. Delta V E times delta X is not going to work, right? This delta X is changing. Delta X is changing as we move in the y direction. So the only way that this delta V remaining a constant must be that this E is changing as we move in the y direction. That delta X, by the way, is going to be D plus y times tangent theta. Okay? So as you move along, this distance between the 2 plates is going to change as D plus y times tangent theta. Okay, now, so I can take this and substitute this over here. Let's go over here. This is going to be from 0 to L. That sigma is epsilon naught times E of y times L dy. This E of y, using this, is delta V divided by delta X. So 0 to L, epsilon naught, delta V divided by this delta X is D plus y tangent theta. And theta, there is an L, and there is dy. Okay, and this is our charge Q. Now, as you see, we managed to obtain an expression that's proportional to delta V. So when I take this ratio, the delta V's are just going to go away. Can I take this integral? Now, this epsilon naught can be taken outside the integral. Delta V can be taken outside. L can be taken outside. This is 1 over x plus a constant. The integral of that is just a logarithm. Right? So let's take that integral. I'm going to raise this part. Okay? Just because I don't have enough room anymore. So Q is going to be epsilon naught delta V L. The logarithm, the integral of that is just a logarithm. That is D plus, let's call this y, D plus y tangent theta from 0 to L. So this is going to be a difference of logarithms, and difference of logarithms is the logarithm of the ratio. So this comes to epsilon naught delta V L logarithm of the, at the upper end, it's going to be d plus L tangent theta, divided by the lower end, it's just d. This y being 0. Okay? And of course, then the capacitance is just this divided by delta V. It's epsilon naught L, logarithm of just the same thing over here. Okay. So this is the capacitance that we calculate. Now you can take this and simplify this a little bit further. First of all, because theta is small, this is going to be just theta. Tangent theta is approximately theta. Furthermore, this is a small number, and if you just divide this out, you're going to get 1 plus a small number, and the logarithm of 1 plus a small number is a simple expansion. I think it's logarithm of 1 plus x is x minus a half x square something something. Okay, so the logarithm does not have an expansion around 0, but it does have an expansion around 1, so you can just use that one. I think it's given in the appendix in the book somewhere, but you can leave it this way. Okay, so this is the capacitance that we get. Now, how about the other way? How about if we just think of this as capacitances, as capacitors that are connected in parallel, infinitely many infinitesimal capacitors that are connected in parallel. So let's take a look at that and see if we obtain the same result. So to do that, I actually need to remember d plus L tangent theta divided by d. And let's see if we actually get something similar. So for this, the total capacitance is going to be, instead of having sums, we are going to have an integral. Okay? And integral is just going to, those little capacitances are going to be just the capacitances of these little parts. Okay? So this dc is going to be epsilon naught, some small area, dA, something we already know, plus y tangent theta. Okay, so this is the delta x. Again, so this is just the epsilon naught, the surface area of that capacitor, which is infinitesimal because it has infinitesimal thickness, divided by the plate separation, which is d plus y tangent theta. Okay, and now we need to again write this in terms of y, so we can actually take this integral, with this y being in the denominator, and we proceed in exactly the same way. So epsilon naught is going to be over here. It's just L dy d plus y tangent theta, and you integrate this from y equals 0 to y equals L. 0 L dy by d plus y tangent theta. And of course, this is the same expression that we had before. That expression had the delta V there, but then we divide out by delta V. We're trying to calculate the charge, the delta V. So this is delta V. It's going to give the exact same expression. Okay? So you can proceed either way. Obviously, this is easier. You're giving the hint that using the hint that they give you. But this is like a trick rather than a technique, that you can't really use this all the time. The other approach, starting with the definition of the capacitance, this is the charge per potential difference, and try to express this charge, turn this into something related to electric field, which then is related to the potential difference, is something more general. Right? We usually go this way. We manipulate delta V and get something proportional to Q. In this case, we manipulate Q to get something proportional to delta V. But of course, because the hint is given, this shorter way is perfectly feasible as well.